Let's take a look at a term that has a different meaning in everyday language than it will in physics, or at least slightly different. It's the term acceleration. In physics, acceleration will be the rate of change of velocity. In everyday language, acceleration is usually taken to mean speeding up. And if we're not speeding up, we say we're not accelerating. But we'll find out in physics that there are actually other ways to accelerate as well. We'll begin this little section with a discussion of average velocity, and I'll do a calculation for that. Turns out for this quarter at least, every situation we look at will either have zero acceleration or constant acceleration. And in the case of constant acceleration, the average is equal to the instantaneous. Average acceleration is defined to be this, a average dash x. This would be average acceleration in the x direction. We'll add more dimensions soon. It would just be v2x minus v1x. These are the velocities at a time 2, the velocity at a time 1, and then divided by t2 minus t1, which can be simplified to delta v sub x. This is the change of velocity in the x direction, divided by the change in time. The numerator is the change in velocity. The denominator is the change in time. When you calculate that ratio, you get the rate of change of velocity. Now, it's possible for v2x to have a smaller value than v1x, in which case we'd get a negative value for the acceleration. In the everyday meaning of acceleration, outside of physics, we would say something isn't accelerating if it has a negative acceleration. But in physics, an object is accelerating any time its velocity is changing, whether it's slowing down or speeding up or changing direction. Let's do a sample calculation for average acceleration. Let's suppose that at time 1, the velocity in the x direction is 5.0 meters per second. It's got a plus sign, so I know it's going in the increasing x direction. v2x, that's the velocity at time 2, would be 17.0 meters per second. And these are just numbers that I made up. I happened to invent them so that the calculation could be done in my head. Let's suppose that t1 is when we start our clock, and t1 is 0 seconds. t2 is 6 seconds later, and that's when the thing has that velocity. The acceleration here average acceleration in the x direction is going to be this formula up here, which would give me 17.0 meters per second minus 5.0 meters per second divided by 6.0 seconds minus 0 seconds. And if we do this calculation, we get 12.0 meters per second on top and 6.0 seconds on the bottom. Be careful with the units here. I can do an example in class where I show you that those seconds don't divide out. In fact, we could write this as 2.0 meters per second, and in many parts of the world, this is the way you would hear acceleration stated, that it's 2.0 meters per second. That's not a bad way to say it, but in the United States, we tend to write it this way. It would be 2.0 meters per second squared. Right? That's not quite as clear a way of stating it. Algebraically, it's absolutely correct to write it this way. But when we say the acceleration is 2.0 meters per second, what that tells us is that every second this acceleration is maintained, the velocity will change by 2.0 meters per second. So the velocity change rate is 2.0 meters per second. Still, we say 2.0 meters per second squared in the US. And that's a simple average acceleration calculation there. Now, we're going to immediately move into instantaneous acceleration. And if you read the book on going from average velocity to instantaneous velocity, the process is the same here. For instantaneous acceleration, the expression is a sub x, we don't need the AV on there anymore because it's not going to be an average, will be the limit as delta t goes to 0 of this expression, delta v sub x over delta t. And in calculus, you'll learn soon that this particular limit can also be written as dv sub x dt. By the way, if you've never seen a limit before, you're going to see one soon in calculus, and so that's why I'm not going to bother to explain that here. I can show you this graphically though, and here's what can be going on. Let's suppose that we have a graph of v sub x versus t, and maybe the graph does something like this. And we would like to know what the acceleration happens to be at some instant. And let's suppose that this is the instant when we want to know what the acceleration is. Well, we could calculate the acceleration or the velocity here and the velocity here. If we did it at those 2 points, and we would get a delta v that goes from here to here, a delta t that goes from here to here, and we could take that ratio and that would give us the average acceleration between these 2 points. But it may not be a particularly good estimate of the acceleration at this point. So we pick 2 points that are closer together. Pick some that are like this. And now we'd have a delta v that's a shorter thing. We'd have a shorter time interval here, delta t, and we'd calculate the ratio delta v over delta t over this smaller interval, and maybe we'd get a better estimate of the acceleration. Well, if we keep shrinking that interval, shrinking the time interval, eventually we'll have a time interval that just barely straddles that point in question as delta t goes to 0. And when we do that, then we'll get the instantaneous value of the acceleration. And we look at that limit as delta t goes to 0. That would be the instantaneous acceleration. There's a set of constant acceleration equations that we'll find very useful. We'll use them throughout the year in this course in various ways, and they'll be useful in a way that the equation that we developed yesterday for constant velocity is going to be useful in certain situations. The constant velocity equation looked like this. We had that x was equal to x naught plus v sub x times t. And that's a nice handy equation when we have constant velocity. Let's see what the ones look like for constant acceleration. First of all, we'll start off with looking at an expression for the change in velocity when we do have constant acceleration. The acceleration will equal some v minus v naught over t minus 0. Now, I made up a particular thing here. V is going to be the velocity at some time t. V naught, that's the way we say it, v sub 0, but we say it v naught, is going to be the velocity at time 0. And if I rewrite this expression, I don't have to have that minus 0 on the bottom, because when you subtract 0 from something, you don't lose anything. So that's what this turns into. If I do a little bit of algebra with this expression, I get an expression for the velocity that looks like v equals v naught plus at. So that's our first constant velocity equation. This is one that gives us velocity as a function of time. If you were to graph this, you get something pretty interesting. I'm going to pull in a piece of scratch paper here to graph it on. Actually, I'll just write on the back of the last thing. That's the equation of a straight line. This is v as a function of t. And let's assume for the moment that we have a positive acceleration and a positive value of v naught. The line that we have here is going to look like this. This is v versus t. This would be the line. V equals v naught plus at. The vertical intercept here would be v naught. The slope equals a, the acceleration. In that equation that we had yesterday, this one down here, when we graphed that, that was the constant velocity situation. We had a graph of x versus t, and I'll just suppose here that I have a positive velocity, and maybe I'll have a negative value of x naught here. Okay, x naught is the vertical intercept. That's the value of x when time is 0. The slope here is equal to v sub x, and that line is the line of x equals x naught plus v sub x t. So here's the deal. When you have constant velocity, an x versus t equation is a straight line. The vertical intercept is x naught, the slope is v sub x. When you have constant acceleration, a v versus t graph is a straight line. The vertical intercept is v naught, the velocity at time 0. The slope is a, the acceleration, and that's the equation that we're graphing here on the v versus t graph. But with this constant acceleration, what is the x versus t graph going to look like? Well, we need to graph that. It can look like various things depending on the values of x naught and v naught, but the curve ends up being the curve of a parabola, and it'll be some kind of a parabolic curve here. In this case, it isn't the slope of the curve that will tell us the acceleration, it's the curvature of the curve, which is kind of a complicated looking thing. But this will be the graph of this equation, x naught plus v naught t plus 1/2 at squared. And as you learn more in calculus, you'll learn how you might be able to arrive at this equation. It'll actually take some of the things that you learn in second quarter calculus, but you can actually develop this equation fairly quickly. We can also do it using some algebra, and I'll show you an algebraic technique for getting this thing. These are the two usually used